Hello.
Very good afternoon, dear participants, and welcome back to the third session of the third day of Atal Academy sponsored 1 week online faculty development program, Photonics, organized by Department of Physics, Electronics and Photonics, Rajarshi Shahu Mahavidyalaya, Latur. Today, for this session, we have a eminent professor, Professor Anchal Srivastava, for delivering a talk on the topic, very important topic, lasers, holography, and LIGO. I request one of the participants, Dr. Bharti Patil from Mumbai, to introduce our today's guest, Dr. Anchal ma'am. Bharti Patil ma'am, please.
Okay, thank you, sir. Good afternoon to all of you. Myself, Dr. Bharti Patil. I'm requesting here with all the participants to mute your microphones. I'm requesting all the
Please continue, ma'am.
Okay. So at the outset, I would like to thank the Sanstha Shiv Chhatrapati Shikshan Sanstha of Rajarshi Shahu Mahavidyalaya, Latur, for this program, which is sponsored by AICTE Training and Learning Atal Academy. And especially I thank Dr. Abhijit Yadav, who has contacted me and invited me for this lecture. So today we'll talk something about lasers, holography and LIGO. This subject is very vast. My talk is containing 3 subjects which are pretty widely encompassing, even individually. So we'll try to take it up within the given time. Now, firstly, I would like to pay homage to my gurus who introduced me to lasers, holography and nonlinear optics. Firstly, since the corona times are here, I would like to show this slide because there is always a similarity between what is given in nature and what we find later in nature, which is obvious. It is the macro thing we are seeing, and it is also the macro thing, and this one is the very, very micro level thing, which we are very much afraid of these days, the COVID-19. So there is a similarity, and I am showing this because if we are vigilant enough and watchful enough, observant enough, we can see whatever there is in macro that gives us some hint about the micro things. So firstly, I would like to orient all the participants towards lasers and optics. So I'm showing this slide, which is containing the table, which is a vibrationless table, you can see, and these points are actually, these are holes with screws in it, and you can fit any mount on these tables. These tables are pneumatic tables. They are resting on pillars which are floating, and the table is floating on air, so that any disturbance, any vibration can go away in air and it will not affect the setup, your optical setup. So this is called vibrationless tube. In my next some disturbance is coming, Dr. Yadav, some disturbance is coming. So in this next picture, we can see that vibrationless table even more closely. We can see there are several optical elements, like this one is prism, this is lens, and this is laser beam is coming, and we have reflectors over here, we have beam splitters also. So you can see that we can set up a complicated optical setup on this table, and we need not do this thing in a linear form. Generally, all optics has to be done in linear form because the light travels in a straight path. But here we can have a complicated setting which is not linear, and therefore a big experiment can be set up in a small space. This is another slide which can motivate you for optics. And this is another slide on the same vibrationless table. This laser is here, and you can see this pretty beautiful laser light coming outside, which is not diverging. Here you are using some lens, and it is getting a little bigger. The spot size is getting bigger. Again, it is converging over here and coming to this place. So all these setups are nowadays available, and they are really interesting to make a study upon. This is particularly a tweezers beam part. Tweezers are very interesting. I'm not going to dwell upon it today, but tweezer means it is just like scissors, pair of scissors. Tweezers can be used to navigate a certain very small molecule at any path you want. This is again a big assembly, very big assembly for this optical studies. Then we come to lasers. Lasers, as we all know, but we should repeat it. It is acronym of light amplification by stimulated emission of radiation. So each word has meaning. Stimulated word is very intriguing, and we'll see what does it mean right now. In 1958, even before this, Einstein predicted those A and B coefficients. He gave his A and B coefficients, which told about spontaneous emission and stimulated emission. Later, that was a theory. Now, later in 1958, Shallow and Towns proposed the construction of laser, and immediately after, in 1960, a laser came, which was a solid state laser and which was ruby laser. Now, ruby, many of us will be knowing, it is a crystal. We are using it in ornaments also, so you can get it at some crystal shop or a goldsmith shop. So ruby has pink color, and this pink color comes because of chromium. Ruby means alumina doped with chromium. So aluminum is also a valency 3 material, valency 3 metal, and chromium is also +3, and you are doping chromium in this. So it is replacing some of the aluminum. A very small amount of chromium is doped in alumina, which imparts a pink color to alumina. Otherwise, alumina is white. So it imparts pink color, becomes a ruby crystal. A red, it is written here. In this ruby laser, a 2-inch long rod was taken. Its ends were polished, and then it was used in the laser. In 1961 came the HENI laser, helium neon laser, which was a gas laser. You can see this ruby was a solid thing. This helium neon is a gas laser. So just 1 year after, this laser came. Now, key to successful laser operation is the active medium, which amplifies the electromagnetic wave. Active medium. So here we can see the active medium is the, here it is solid, the ruby rod, and then here it is gas. So this is the active medium. Gas you have to choose, which gas you have to take, which crystal you have to take, or which liquid you have to take. That you have to choose, and you will be choosing all these things by doing the spectroscopy of those materials. By spectroscopy, you will be able to know that, by emission spectra, you will be able to know that which wavelengths are being emitted from this crystal or from this material. And by absorption spectroscopy, you will be able to know which wavelengths are being absorbed. By knowing this, you will be able to know about the energy levels of the medium. And those energy levels are very important for us, because we have to know the lifetime also of the energy levels. In general, you know the lifetime of dipole relaxation is 10 to the power minus 8 seconds, which is very small. But there are some energy levels which have longer lifetime, and they are called meta-stable. And they have longer lifetime. They can have a much longer, 1,000 times longer lifetime, that is 10 to the power minus 3 seconds also they can have, 10 to the power minus 6 seconds they can have. So we have to choose, any material has many energy levels, so we have to choose at least 3 of the energy levels in which one of them should be long-lived, that is metastable state. And this is ruby is a 3-level laser, and you can also choose 4 levels in which one level is metastable And helium neon laser is an example of a 4-level laser. So there is some advantage, big advantage with 4-level lasers over 3-level lasers that I'll be telling you in due course of time. Now, active medium is a material which fluoresces or exhibits luminescence. So you have to choose materials. You have to see their luminescence spectra also. The materials can be gases and their mixtures. Individual gas can also be there, just like carbon dioxide lasers also we have. Helium neon laser is a mixed one. Then argon ion laser is a single one. Like this we can have gases individual or their mixtures. We can have crystals or glasses doped with ions. Here I think you should mark that, you should note the difference between these two. When you say crystals, that means you are talking about the crystalline materials. When you say glasses, you are talking about the amorphous materials. Those two are fundamentally different, very different to each other, and therefore they give rise to quite different properties of lasers. So you can use, just like one example I'll be telling you, you can have ND YAG and you can have ND glass. ND means neodymium, YAG means YAG, yttrium, aluminum, garnet. So you are doping neodymium in the yttrium, aluminum, garnet crystal. And you can have, at the same time, you can have ND glass also. That means you are doping neodymium ions in the glass. Glass is amorphous. So both will give you a difference in properties of the emitted light. Other materials can be liquids. Liquids are mainly dyes, not like any solution you take. That will not work as a laser, that will not give you laser light. But these dyes can give you laser light because they have a particular type of energy levels and they have intersystem crossings, etc. And they can give you laser light. Then later on, these days now you have semiconductor lasers also. Means semiconductors, like you have seen, you might not have seen semiconductor laser, but you have seen semiconductor diodes. In every electronic gadget of yours, there is an indicator. A red light is blinking, or a green light is there, or a blue light is there. So they are LEDs, light emitting diodes, and they are made up of semiconductors. That means semiconductors can emit light. So whichever substance can emit light can be used as lasers. However, we have to study other properties of it. Now, nextly, you can have polymers also. You can use polymers also as lasers because you can engineer polymers which give you fluorescence. So whichever element is giving, whichever material is giving fluorescence can be used, may be used. It is a potential candidate for lasers also. And lastly, the most intriguing thing is free electrons. Free electrons can also be used as material for lasers. So all these lasers, these 5 materials, they come in conventional type. And this free electron is totally different. You can say it is a little bit exotic. Free electrons, they are totally different. The physics is different. And as you know, that all the materials have energy levels, and those energy levels are characteristic of those materials. That means everything is fixed. If you take material A, you will get certain number of energy levels. If you take material B, you will get another set of energy levels. And the difference between energy and the difference of energy between these energy levels would be different for the material A and for material B, but fixed for material A and fixed for material B. So whenever you work with material A, every time you will get the same wavelength, say lambda 1. When you work with material B, you get emitted wavelength as lambda 2. But same as every time you will get lambda 2 only. You will not be able to play with the wavelength. But in case of free electrons, you are totally free. You can play with the wavelength. You can start from visible, you can go to near infrared, then you can go to microwave, radio waves that I have not seen. Radio wave I will not say, but till microwave I have seen. And on the left, you can go to ultraviolet, and these days you can go to X-rays, not only soft X-rays, but hard X-rays also. So we'll discuss it later. Now we'll see the examples of solid state laser. Ruby and ND are very common examples. For gas, we have helium neon, helium cadmium. For organic dyes, we have rhodamine, we have coumarine, we have xanthine. Those participants who are from chemistry, they might be knowing it even more closely, that what these dyes can do. Then we can have molecular lasers also. This molecular is actually using gas. You can put it under gas also. So molecular lasers are, one carbon dioxide is one of the examples. Excimer. Excimer is a combination of two words. EX means excited and IMER means dimer. Excited dimer, and combined form gives you excimer laser. That means when it is excited, it exists as dimer, means two. It exists as two atoms making a molecule. They are dimer, and when it is in lower state, lower energy state, then it is dissociated. When it is in excited, it is dimer. So this is very interesting. Excimer is also very interesting because it gives you population inversion. Because when it is excited, it is dimer. In lower energy state, it is not a dimer. That means if you take dimer as a reference, that means you are seeing a population inversion of dimers. Population inversion means whatever is natural, that is not happening, but some inverted thing is happening. That means in the lower energy level, there is nothing, and in the excited energy level, there are electrons or atoms. So this is quite inverse to natural, because you know in natural phenomena, everything wants to be in ground energy level. So these excimers are also very interesting kind of lasers. Then plasma. Plasma, you know, it is the fourth state of matter in which everything is a mobile, means plus and minus, both the charges are mobile. At least one should be mobile, but they are in ionized state. So we can have ionized vapor of magnesium, calcium, strontium, barium, and they can luminous and can give you a material for laser. Then semiconductor laser. This is interesting. Everybody should think of that why we have a PN junction which is rectifying. It is made of silicon or germanium. But here it is not silicon or germanium, neither silicon nor germanium. It is something different. It is a compound semiconductor. Gallium arsenide, indium phosphide, indium arsenide, indium antimonide, gallium arsenide phosphide, like this. Indium gallium arsenide also. So you can have two or you can have three of them mixed. You can have four of them mixed, and you can keep on researching over this. So semiconductor laser, these are giving you light, whereas that silicon and germanium was not giving. So it makes a thing of study for everyone to revise and brush up their previous studies, that why these semiconductors are being used for laser action. Now all these lasers which I am discussing now, solid state, gas, organic, molecular, plasma, semiconductor, all these lasers are operating in oscillator mode. So this oscillator mode need to be understood. What can be the other mode? The other mode can be amplifier mode. So as we know, what is oscillator? Oscillator is something which can generate a signal. Oscillator is something which can generate a signal from nothing. There was no signal, but the oscillator circuit can generate a signal. Whereas amplifier will do, what will it do? There is a signal coming from somewhere else and the amplifier is amplifying it. So this is the basic difference. So if you don't have anything in the oscillator mode, you cannot amplify it. So the more basic thing is oscillator mode. All these lasers operate in the oscillator mode, and in this they have bound electrons, which I told you earlier, that every material is having its own set of energy levels, and the electrons are bound to move, or electrons are bound to make a transition from a fixed energy level to a another fixed energy level. That means they are bound. They can't do anything freely. They don't have freedom. They have to make a transit between those energy levels only. That means they are bound electrons. Whereas in the free electron laser, The electrons are totally free. They can go anywhere. They can go and strike the wall also. They can go in a particular channel also. That will depend upon your experimental setup arrangement. So therefore, since these free electrons, as we know that freedom is very important. When we have freedom, only then we can exhibit our, or we can flourish, we can exhibit our talents and we can use our inner talents when we are free. Similarly, when these electrons are free, they can be used for emitting a range of frequencies, and therefore we call that the free electron laser is tunable. You can tune it at any frequency, and this free electron laser can be operating in both the modes, in oscillator mode as well as amplifier mode. When this free electron laser came way back in around 1970s, it came, then it was used in amplifier mode only, because we were using the radiation from these lasers, conventional one. We were using the radiation coming out from these lasers as an input to the free electron laser, and the free electron laser setup was amplifying those energies. Okay, but of late we have started, means of late means you can say 20 years or so, we have started working in oscillator mode also, and therefore now we are able to generate X-rays also from free electron. X-ray laser also we are having. Since you know that we are not having any X-ray laser from these conventional lasers, because between the energy levels a transit cannot produce X-rays, and therefore no X-ray laser here. Here we can have X-ray laser because the free electron can be of very high energy. It can be accelerated to very high energy using the betatron or the microtron, depending upon the current value. Current means high current. So depending upon that, you can use an electron accelerator. You can accelerate it to very high energy level. Its velocity can be very near to the velocity of light. Let us say 0.999 c. You can have that. So at that much high velocity, the electron will have a very high energy and it will emit a radiation. You know that accelerated charges always emit radiation. So those electrons will also emit radiation, and because of certain arrangement, they all will be coherent, they all will be in phase, and you will be getting laser radiation at very high energy, as high as X-rays. Now we'll understand I shouldn't say you all are teachers. So I can say that we'll revise these concepts. Absorption of radiation or light. So on the y-axis, permanently it is shown, it is energy on the y-axis. Okay, so we have plotted two energy states. One is the lower energy state, other one is the higher energy state. In lower energy state, suppose there is an electron sitting over here, a photon comes from outside. Okay, and that photon is absorbed by this electron. Electron absorbs the photon, it gets energy, it goes to higher energy state. You might be thinking it is so simple, why I am telling about it, but you have to look at it very closely, only then you will be able to appreciate the fundamentals of lasers. So the electron is in lower energy state. Yes. Electron is in the lower energy state, and by absorbing the photon, it is going to the higher energy state. Now the situation is like this. There is nothing in the lower energy state, and there is one thing in the higher energy state. That means you can say the population has been inverted. No population in lower energy state, population present in the higher energy state. So this is a situation, this particular picture is a situation of population inversion. Okay. Now we come to spontaneous emission. Spontaneous, you know the meaning of spontaneous. anything which happens suddenly, that is spontaneous. So you again see, if this is a situation of population inversion, electron in the higher energy, nothing in the lower energy, but you know that after 10 to the power minus 8 seconds, this electron cannot remain here. If it is metastable state, it will remain up to 10 to the power minus 6 seconds or minus 3 seconds, but after that, this electron cannot stay in the higher energy state. It has to come back. So it is coming back to the lower energy state. Now it has come here. When it will come here to the lower, then it will emit its extra energy and a photon will come out. So you now see that this is these states are, all these picture are of spontaneous emission. Now spontaneous emission is very important. You have to keep it in mind. I will tell you later that what role does it play in the working of a laser. Then we come to stimulated emission. Stimulated word is very important. I think most of you know this. Stimulated means it is something you are not doing, like you, I will give you one example. Suppose a bird is sitting somewhere and you are approaching to the bird. As soon you start to approach, the bird will fly away. So you have done nothing. You were simply approaching, but the bird flew away. That means that bird got some stimulus and she got fear and she just flew away. So that stimulus is important. What is that stimulus? In this particular example, you can understand what is the stimulus. So similarly, you can stimulate some electrons also to act according to your will. Okay, so that is the stimulated emission. Again, the same thing has to happen. Electron in lower energy state, it absorbs a photon, goes to a higher energy state. Okay, now two things can happen, either spontaneous emission or stimulated emission. Spontaneous emission will anyhow happen because it is a natural phenomenon. Stimulated is not a natural phenomena that we have to do. So for stimulation, we are bringing a photon and we are trying to use, just think as we are trying to hit it so that it may move to lower energy state. But now the energy of this photon is very important. What is the energy? The energy is the difference of these two states, lower minus higher, or you can say higher minus lower. So the difference, suppose this is h nu, so this photon is of energy h nu, it will come, it will stimulate this electron, and this electron will immediately jump down to the lower energy state, and while jumping it will emit a radiation, or you can say it will emit a photon, and you can see here that another photon is emitted, and this is this original photon which was used to stimulate. What do you actually notice in these two? There is a handicap of talking with the participants. Every time I will ask, you will not be able to answer because perhaps you are muted. But this is very interesting if you note that what is the similarity between two photons. I hope you have noted it. It is, you can see the maxima of both are lying over each other, minima are again lying, maxima are again lying over each other, minima again lying over each other. That means what I want to say, they are in same phase. They are in same phase and you can say both are coherent. So keep this in mind. Stimulated, man-made thing, spontaneous is a natural thing. Spontaneous is very important for laser. People say stimulated is very important. Stimulated has to be there that you are making, but if there is no spontaneous, you cannot make a laser. So I would say spontaneous emission is very important. So I have made these two slides in one slide only to compare. You can now compare. In spontaneous, this one photon is going away. In stimulated, now there are two photons, the original one and the emitted one, and both are in phase. So now here I should tell you what is the utility of spontaneous emission. Now I was saying that you bring a photon of energy h nu, which is the difference of these two states. But from where will you bring? Because you are going to make a laser. So from where will you get a similar laser even before making it? How can you get? So that you can get from nature only, and that is the spontaneous emission. When it will jump here, give a spontaneous emission, that spontaneous emission will later work as this photon, and it will stimulate further, and stimulated emission will take over and your laser will be coherent. If the spontaneous emission takes over, then your laser, you can't get a laser. It will be an incoherent radiation. But because of your further arrangements, the started with stimulated emission, but later on took over by the stimulated emission. This is a picture of ruby laser, which is a 3-level laser. This is a cross section. You can see longitudinal cross section. This is a 2-inch ruby rod, which is alumina doped with chromium. And you can see there is a helical type of thing, which you see these days in compact CFLs also. This is a glass spiral. And you see this glass spiral is attached here with battery, power bank, and again the other one is attached here. So when this is put on, there is a flash of very high energy, very high intensity, not energy, very high intensity, and that flash goes inside the ruby rod. When the flash goes inside the ruby rod, it excites the electron, and the electron go to higher energy level, and after 10 to the power minus 3, minus 6, minus 8, whatever is the setting, they come down and they give you some light out of it, which is shunted back and forth in the laser cavity, and finally it comes out and gives you laser. Earlier you saw 3-level laser, now I will show you 4-level laser, and I will emphasize on the advantage of this 4 levels. Here, see here, these are 4 levels, E1, E2, E3, E4. In every level there are some electrons. Why? Because it is at room temperature. Due to room temperature, they get energy. How much energy? K, T. K is the Boltzmann constant, T is the temperature. So they are getting energy and they are jumping to higher. But you see that in the highest energy level, there are only 3. That means very less electrons here, and most of them are in the ground level. Now you give photons from outside, they will absorb, they will go up. Now when this action is called pumping. You are pumping, you are giving energy. Just like while pumping you put air in the tire tube. So here also you are pumping the electrons by these photons. So pumping has been done, electrons came up to the E4 level, then eventually they will drop. After their lifetime, they will drop to E3. Now you see this. Between E3 and E2, there is a population inversion. Or E3 and E1, population inversion. E2 and E1, there is a population inversion. ठीक है, ऊपर population ज़्यादा है, नीचे कम है, so there is a population inversion. अब जब population inversion है, all these from sitting in E3, they will come down to E2. And from E2, they will relax to E1. So our laser level would be E2 and E3. They would be main here, not the E1. So what's the use of E1? The use is that eventually this atoms in E2 will come down to E1 and E2 will be depleted. And therefore E2 will remain empty. So when E2 is remaining empty every time, and E3 is populated because of this pumping, E3 is populated and E2 becomes empty and empty, then there is always a population inversion maintained between E3 and E2, and therefore we have to do less of pumping, and that is the advantage of 4-level laser over the 3-level laser. More of it can be explained you if I give you the equations also, and if I show that will come to the conclusion that if even one atom goes to the upper level, then a population inversion can be achieved. Whereas in 3-level laser, at least 51% should go above, then only a population inversion could be achieved. So this is the advantage. Same thing is explained here in this picture. Now I come to helium neon laser, and this is the longitudinal cross section. You can see that helium neon gas is filled. This is the glass container. Helium neon gas is filled in it. One side is anode, another side is cathode, and there is a mirror. You see it is a high reflector. High reflector, we'll say it is a 100% reflector. None of the light can escape from this side. Light has to be reflected and it has to come to this side. This reflector is, you can say it is 99 point something or 98 point something reflection it is providing, and therefore a certain amount of laser light can escape through it, and therefore it is named as output coupler. That means it is coupling the light to the output, and this laser output is coming from this side. But before coming, the laser light is shunting between this mirror and this mirror, back and forth, back and forth. Back and forth, back and forth, it is shunting. So, because of that shunting, the laser light grows, because during shunting, it keeps on interacting with the active material and attaining energy more and more, more and more. And due to this particular laser cavity are also of various types. They can have plane mirror, they can have convex mirror, plane and convex, then convex and convex, and so many. So they can, they also affect the frequency, which without mathematics you will not be able to understand. So, but you remember this, that the type of cavity, the type of mirror at the ends, they will determine the modes which are coming out, and the modes will determine the frequency. I hope you all know mode, what mode is. Mode is a simple word that means way of something. Like sometimes you say that what is the mode of money transfer. Sometimes you say transfer it by draft or by check or by RTGS these days. So these all are modes, the way in which you do something. So mode of light ka kya matlab hua? Mode of light means the way the light is propagating. It will propagate in a certain container or certain cavity according to the dimensions of the cavity. Suppose there is no plate over here, some mode will escape, light will go outside. From here also light will go outside. So that means that mode has escaped and that mode has been lost. So we plan the cavity accordingly, that which modes are to be kept and which modes are meant to lose. This again a picture, you can see this helium neon laser. It is some experimental setup. You can see here there is a dot over here. So this lasers are always very pinpointed and they are not diverging, which is one of the most important property of lasers. This is you can see it as a dot over here. These are the partially reflecting mirrors. They can also be put at Brewster windows. If a Brewster window is kept here, you know what is the use of Brewster angle. This will make the light polarized, and you can have polarized laser also. You can have randomly polarized laser or you can have linearly polarized laser. This is picture of ND arc. This is ND arc actually gives you 1064 nanometer, and that is in the infrared. So again, these are fully reflecting mirror. This is partially reflecting. Some flash tube is here which is pumping it, and you are getting laser output. Here I should also mention that in the solid, so in the solid lasers which are using crystals, you cannot send a current in the solid things, and because they are not a conducting thing, they are crystals. You cannot send current, so they cannot be pumped using electric current. They can be pumped using optical methods, and therefore you see in Ruby also, In ND-arg also, there is a flash tube written over here. You are using a flash tube to pump, means you are using optical pumping. Whereas in helium neon laser, you saw there was an anode, there was a cathode. If you come here, there's an anode, there's a cathode, and you can attach it to a electric field and a current can flow, a current can excite the atoms of the gases. That means it is using electrical pumping. So gas laser can use electrical pumping, but crystal laser cannot, and it uses optical pumping. Now use of one of the use of laser, you can see this is interesting. This is retroreflector. This is the surface of moon, and this retroreflector has been placed on the surface of moon by Apollo 11. Okay, then later on Apollo 14 went, Apollo 15 also went there, and they put an array of, this is an array of reflectors. So these are there on the moon. So when you are here, you can see some laser is come. This is a laboratory, some laser. This is perhaps the photograph from China, perhaps. So this laser is coming out and it is going to moon. You can see it is not diverging. It is going to moon, and on moon it goes to the reflector. From there it reflects and comes back to the laboratory again. So you can record the round trip time, how much time this laser has taken in going to the moon and coming from back to the moon. You take it and you know the speed of light as c, and you can calculate the distance between Earth and moon using this. Now you should also understand the meaning of retro. What is the meaning of retro? You all are teachers, so I think you know how much it is important to get answers from the audience. But again, this is a handicap of online. So retro means when you move on the same path. When you move back on the same path, that means retro, same path. So you know that what reflection kaise hota hai, you know when the light comes, it is reflected at the same angle. Angle of incidence is equal to angle of reflection. So light comes from a direction and goes to other direction. But in case of retro, what happens? The light comes on whichever line, it goes back on the same line. So it is a retroreflector. So you see this is kept on the moon for experiments like this to measure this is called laser ranging experiments. Okay? You can use laser for this. Now properties of lasers. The first one is directionality. You had seen in the earlier picture that the laser is not diverging. It is going exactly in a straight path without diverging. So only axial and paraxial rays are reflected back and forth. This is the property of your cavity, that only axial and paraxial rays are reflected back and forth in the cavity, and the other rays are lost away. So you have only directional laser coming out, and all the extra modes have been lost. Lost means that is to our benefit. That loss is not actual loss. That has been made specifically, that loss has been designed specifically to get a directional beam. Monochromaticity. Mono means single, chrome means color. Monochromaticity means single color means single frequency or single wavelength. So this is again a property of laser. But here I should mention that no light is monochrome. No light is actually monochrome, but we say lasers are monochrome because monochromatic, because it is, the line width is very less and it is highly monochromatic compared to other lights. So we use the word monochromaticity. But if you come, actually it is not a single wavelength, it has plus minus omega omega, not plus minus omega. It has something plus minus, maybe 5 nanometer plus minus, 2 nanometer plus minus, but there would be a some width. But still we call it monochromatic. So this is a property. Monochromatic resonator allows laser oscillation at selected frequency. Again, this property of laser is an outcome of the design of the cavity, or that cavity, or you can say it resonator. We call it resonator. We don't call it cavity because it is open from, it is upper plate and lower plate is open. There is no upper lower plate. Only two mirrors in front of each other. So we call it resonator instead of cavity. Cavity is a closed one. So because of this design, we lose unwanted laser oscillations and monochromaticity appears. Third thing is coherence. Coherence means it is emitting in phase and it is having coherence are of two types, temporal coherence and spatial coherence. When there is a temporal coherence, it gives rise to monochromaticity. You can, temporal means in time, and in time it can be coherent when it has one wavelength only, otherwise it can't be. So the monochromaticity leads to temporal coherence. And the spatial coherence comes from the directionality and the focusability. And because of the focusability and directionality, that means it is very faithful. If you are sending it theta equal to 2 degree, it will go to theta equal to 2 degree only. It will not diverge and it will get focused on that point only. Because of that, you can use it in the subcellular surgery. You know very well that these are being used in ophthalmic surgery also. And this coherence time is of the order of 10 to the power minus 3 seconds. It is quite a big time. Minus 3 seconds ka matlab 1 millisecond, which is a big time for doing experiments. Quite a long time. Coherence length can also be calculated by multiplying the coherence time with the speed of light, and you can see it is 100 kilometer. That's why I was saying that coherence time 1 millisecond is quite large, because it gives you coherent length of 100 kilometer. That means you can set up an interference experiment over a range of 100 kilometers. Coherence length is very large, and you can very well understand that this is several orders higher than the ordinary sources, like sodium is one of the monochromatic sources. Compared to that, lasers are having several orders of higher, several orders longer coherence length. An example of tunability, gas lasers are having narrow line width, like helium neon laser. It is emitting 6328 angstrom, or you can say 632 nanometer. 630 भी कह सकते हैं. So it has narrow line width, means it is highly monochromatic, whereas in and fixed value. Whereas in dye lasers, you can tune the output wavelength from ultraviolet to infrared by using different dyes, not a single dye but different dyes. Like coumarine dye, you can have this much range, stilbene, xanthine, rhodamine 6G. So they can emit over all these ranges. To make it monochromatic, you have to use some filters to select a particular wavelength out of them. And free electron laser, as I earlier said, it spans almost 90% of the electromagnetic spectrum, starting from X-rays to far IR microwaves also. Something about free electron laser. It is an altogether new and exciting class of coherent optical sources. It has simple and elegant gain medium, means there is no material, it is only electrons. The medium is an electron beam in a magnetic field, that is all. You should have to have a magnetic field and an electron beam which is accelerated coming from a betatron or a microcon. In 1951, You can see this. Our conventional laser came in 1960, whereas Hans Morse proposed low voltage free electron laser in 1951 itself. In 1970, Mayday and his co-workers at Stanford University, they gave the free electron laser, in which they used a 24 million electron volt electron beam, that is, it was accelerated. 5-meter long wiggler. You can imagine 5-meter long means it is going to be a big machine. In those times, it was multi-billion-dollar project and it was not available at many places. Even now, it is not available. Now, these days, our RRCAT, Raja Ramanna Center for Advanced Technology, Indore, now it has come up with a free electron laser. Now, so it is having a 5-meter long wiggler and it is having a beam from carbon dioxide laser for amplification. This is what I was telling you, that free electron laser was initially operated in the amplifier mode, and the radiation which was amplified, that was coming from a conventional CO2 laser. Specifications for that was 43 MeV electron beam, laser at 3.5 micrometer near IR radiation with 300 milliwatt intensity, and the efficiency was very low, 0.01, very low, but the thing started working, and since that day it has kept on progressing. So what is happening? Actually, you are having a big long cavity, 5-meter long cavity. You have a wiggler magnet inside that. I should tell you what is a wiggler magnet. Wiggler word is from wiggle. Wiggle means something like a sinusoidal type of wave, something going up, down, up, down, up, down, up, down. That is wiggling. So that type of wiggler you have to put. Means the magnet is not itself going up and down, but when the electron goes through those magnets, the path of the electron is like wiggling. It goes up, down, up, down, up, down, and simultaneously it progresses in the Z direction also, in the forward direction also, but it keeps on wiggling in the transverse direction also. So those type of, and you can very easily guess that what type of magnets are they. Suppose you put north-south poles, then just immediately you invert it. Where the north was kept, on that side of the axis you keep south, and below the axis you keep north. Again, in the next section, above the axis you keep south, and abhi picture दिखाएंगे आपको, तो you will see it. Then you will get a wiggling action due to simple. In intermediate, we are studying what was the law of force, in which we extend our 3 fingers. According to that, you can see the direction of the force. When you know the direction of current, when you know the direction of magnetic field, you can know the direction of force or direction of motion of the electron, which is along the 3rd finger. Fleming's left hand rule, yes. So you can, when you will invert the poles of the magnet, again the force will be inverted. Again you will invert. Again the force, so the force is flipping again and again, and therefore the electron will experience a wiggling type of motion. You can see the picture here. Here it is written undulator, and undulator means, undulation means the electron is going above on the other side of the axis, coming on the other side, going to the other side, coming to this side. This is called undulation, and this only is called wiggling also. So you can call it undulator magnet, or you can call it wiggler magnet. So it is not a single thing, it is an array. You can see it is written south, north, alternate, and here north, south, alternate. Now this is electron accelerator. From here the electron photoinjector, the electron is being emitted from here, comes to the accelerator, it is being accelerated, and a highly accelerated beam of 0.99 C, a 98 C or 96 C that comes inside, feels the force due to magnetic field and moves like this sinusoidally. And finally what happens when this Wigler array ends? The electron beam goes away because it loses its energy. It loses all its energy to the electromagnetic radiation which was coming from where? It was coming from another laser like CO2 laser. So it loses all its energy to the CO laser radiation from CO2 laser. Now the electron beam falls away and it goes back like this round circle. It goes here, 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 here. Again comes back to the electron accelerator. Again goes here, give its energy to the radiation already present, and then again comes back and again goes into the electron accelerator like this. Another pictures to make the things clear. North south, south north, north south, south north like this, and you can see that electron beam and the input radiation both are written here. Input radiation and the electron beam both are coming, they are propagating with each other. Electron is giving energy to the electromagnetic radiation. The electromagnetic radiation comes out here and the electron beam goes here. It is written spent electron beam. It has spent all its energy. It comes here again, goes back to the accelerator. This is another picture to make things more clear. You can see two mirrors are put at the end. The radiation is shunting between, it is being reflected between this, and finally when the energy grows, energy of the radiation grows. Energy means intensity. Energy to color to hai. The intensity grows, it comes out from this mirror, and this is called free electron laser beam. You can see how much of the mechanical things goes into making this laser. You can see the length. These are the just few examples of the location of these lasers, because this very big project, accelerators, wavelength, peak, power and application. In the Stanford, where it was made, the first laser was made, first free electron laser, we have a 1.2 megawatt and 1 watt laser also. Application is in medicine now. When it was being made, if somebody remembers of the President Ronald Reagan, he was willing to have a space war, and therefore he accelerated the program of free electron laser. But when it went, means his term was over, all these things were turned into peaceful purposes, and the free electron laser was started to use in medicine and biology for research and for medicine also. In USA, you have this. In Duke University, there is one, Vanderbilt, Netherlands, France, Japan, and in UK these days, in UK they are having hard X-ray laser also. Hard X-ray means of high energy. This I can show you, it is taken from the internet. Super laser developed in the UK will help scientists create the conditions found inside planets. Because this laser can melt things, can bring things to plasma state, etc. And this is the report of 2020. Just when this corona came, 19 March 2020. So it is a latest report, and this we call it XFEL because it is an X-ray free electron laser. You see this. It is in Germany. The applications, already I told you, fundamental studies in physics, chemistry, biology, laser spectroscopy, electronics, medicine and surgery. initiating any reaction, controlling any reaction, kinetics of chemical reaction. Kinetics of chemical reaction can be studied using laser because you know that chemical reactions are very, very fast. You put one chemical in the test tube, you put another chemical, you pour another chemical in the same test tube, and you get a result, something new compound. You are never able to see that what happened and a new compound came, because it is so fast that there was nothing to study. So now there are lasers which are nanosecond lasers, there are femto, picosecond lasers which can be used to study the kinetics of chemical reaction, which are actually very, very fast. Kinetics of ultra fast biomedical processes also. Holography, one of the application of lasers. Non-linear phenomena, very interesting, अभी आपको बताएंगे. Nanotechnology also it uses laser at places. Nuclear fusion, that is always thought of for achieving controlled nuclear fusion using lasers, and in defense also. Micro welding, this all we can do. Laser heat treatment for cylinder, gears, etc. to enhance item strength. तो material strength को बढ़ाने के लिए we can use laser heat treatment. Laser cutting, cutting material, cutting paper, cloth, plywood, glass, ceramics, metal. It is used in industry. Fine precise cut, minimal distortion, minimal thermal damage, 2D, 3D cutting possible, automation possible, surgery possible. Now drilling and perforation. If you want to drill a hole of very small diameter, you will use laser and not a mechanical drill machine. Okay? Wear of drills avoided, find deep hole, all these things can be done. Microelectronics applications, welding microcircuits, components, material ablation. Ablation means ablation is important. You can have local material ablation, means you can have local heating. Local heating means a pinpointed heating of a material using laser, because laser can be focused to a particular place directionally, and therefore you can have material ablation. Whole of the material will not heated up, only a particular point, particular area, let us say 1 millimeter area or 2 millimeter area will be heated, and the material would be evaporated or it will turn into plasma, and we have material applications of these things. Isotope preparation also is a big use of laser, where tunable lasers are used. High power laser system for tactical battlefield against missiles, rockets, mortars up to a range of few kilometers. And all this is possible because of high beam quality. That means it is not diverging, it is getting focused, high efficiency, high reliability, long lifetime. Chemical lasers are the answer, but large size due to huge amount of chemical makes it logistically unsuitable. If you use chemical lasers, a lot of chemicals is used and the size becomes big, and therefore it is not suitable for defense purposes. Therefore, solid state lasers, which are very small, can be used for many things. LASTEC has made heat capacity. LASTEC is one of the organization. Not, I should not say organization. One of the lab. It is one of the laboratory of defense. It is the DRDO Laboratory Defense Research and Development Organization का हिस्सा है ये LASTEC. It is in Delhi, and it has made heat capacity solid state laser systems of 400 watt and 1 kilowatt in India, indigenous. Other defense applications are laser range finder, laser range designator, laser warning system, laser altitude, laser seeker, laser delivery, proximity sensor, high intensity laser driven radiation sources. Tabletop high power laser can lead to laser accelerated particle beams. टेबल टॉप कहने का मतलब है कि छोटा सा भी लेजर हम बना सकते हैं. वेरी हाई पावर लेजर का टेरावाट, 150 टेरावाट, विच कैन लीड टू लेजर एक्सीलरेटेड particle beams. We can accelerate it using laser. तो फ्री इलेक्ट्रॉन लेजर में हमने क्या किया था कि पार्टिकल की एनर्जी इलेक्ट्रोमैग्नेटिक फील्ड ले रही थी. अगर हम इसका इन्वर्स कर दें कि लेजर की एनर्जी पार्टिकल ले तो पार्टिकल एक्सेलरेट हो जाएगा. सो वी कैन से वी कैन हैव हाई पावर लेजर्स that can lead to laser accelerated particle beams. Ablative photo decomposition in eye surgery. Excuse me, may I know how much time I have now? Dr. Yadav?
You can, we have a 2 hours duration. You can continue, ma'am.
I can continue. Okay. Now we should know about ablative photo decomposition. Everyone has heard about this LASIK eye surgery. This eye surgery uses Alzheimer lasers. It also uses ND-arc lasers. Interaction of UV laser pulses with solid organic matter, synthetic polymers, bio tissues. These leads to this APD, and it was shown in given in 1982. APD means breaking of a structure of organic solid by photons and the expulsion of the fragments at supersonic velocities. Therefore, some organic solid which is there in body that can be broken up by the use of photons means by the use of laser, and those broken up organic solid can be expelled out. So advantage is precise control over the depth of cut. जितना भी कट का डेप्थ आप चाहते हैं उतना एग्जैक्ट आप कर सकते हैं because all these things are computer controlled, and no thermal damage at microscopic level, and bloodless surgery is there because the laser seals the mouth of the veins and the blood loss is done away with. These are the specifications for laser surgery. I'll not go into the detail. Human cornea can be reshaped by LASIK. LASIK, the full form is laser in situ keratomyelitis. It is well established, and in USA 1 million per year such surgery are being done. Ranging and measurement, we'll skip this. Guided weapons, they are used in defense. Laser transmitted or scattered from pollutant is studied. Hologram of normal object and stressed item gives degree of nature. Hologram, let me tell you. In solid state physics, you can use for spectroscopic characterization of fluorescence, reflection, and backscattering. You can also use it for cancer diagnosis because the cancer cells give red fluorescence when the laser is shined over it. In surgery and therapeutic use, reattachment of retina, reshaping of cornea where Alzheimer laser is used, destruction of malignant tumors, penetration of blood vessels in treating glaucoma, photocoagulation, bleeding ulcer. कभी bleeding ulcer हो जाते हैं and the blood is flowing away, then photocoagulation can be done. Photocoagulation means using the photons, using the lasers, you can coagulate the blood which was otherwise flowing. Lithotripsy, that means we are having stones sometimes in our gallbladder or sometimes in urinary bladder. So we can have lithotripsy using lasers also. Another use, all those was biochemical and was in medicines. Now other than medicines, we can see lasers can be used in sensors. It can also be used in gyroscopic angular velocity measurement. Gyroscope, I should tell, many of you might be knowing. Gyroscope is a sensor that it is an interferometric sensor. The basic is interference is happening inside a gyroscope because there is a source, there is a beam splitter, two beams are coming, One beam is coming directly, the other beam is coming from the disturbed area, some type of disturbance which you want to measure. It is coming from that area. Now these two beams combine, they give interference fringes, and when there was no disturbance, some interference fringes came. When there was a disturbance in one of the beam path, the fringes get shift, and that shift is measured, and you can know what type of disturbance is occurring. But all this can be done due to calibration only. Now these gyroscopes are very highly sensitive. All the interferometric devices are highly sensitive. So this gyroscope is very highly sensitive. If there is a difference or a movement in angular velocity of even 0.01 milliradian, even then the gyroscope will be able to detect. And therefore gyroscopes are generally used in the flying objects like your aeroplane, because aeroplane can go down on the left side, or go down on the right side, or it can dive through the nose. So there are three types of the aeroplane can roll. So there are three types of angular motion in the flying objects, like they are called yaw, roll, and pitch. Yaw means YAW, ROLL, roll and pitch. So yaw, roll and pitch जो है वो these three types of motion, rolling motion in the aeroplane may occur and the aeroplane may crash. So as soon as any disturbance of even 0.01 milliradian occurs in the motion of aeroplane, your gyroscope tells you and you are able to rectify it. And it is also used in all the satellites which are being launched and whatever is being launched in space, just to keep track of the motion and to get it corrected by manually if a person is sitting here, or by auto correction. In ellipsometry also the lasers are used, which is used for measuring refractive index and the polarization characteristics of light and refractive index of some material. So we can have laser in ellipsometry. If you see on the internet, you search, you will see that there are different types of ellipsometry using one laser, using two lasers, and they can be called spectroscopic ellipsometry also. And this is a quite sophisticated instrument in optics. Optics itself is sophisticated throughout actually. Laser cooling, which appears a little bit exotic type of thing, that cooling something using laser. But the concept is simple. Doing it is not simple, but concept is simple, that if you shine a laser on certain atom and the laser absorbs the energy of that atom, the atom will get cooled. Generally we think that if a laser is shining on the atom is getting the energy. But the otherwise can also happen. The laser can take its energy and the atom will get cooled. When it will get cooled, their motion would be minimized. The atom will appear almost still, and you can see the atom. You can photograph a single atom, and those studies can be done by laser cooling. In optical scanners, laser printers, CDs, they are being used. Then optical computer, which people are continuously trying for decades to get an optical computer, to realize an optical computer. They are used because presence of light is 1, absence of light is 0. And you know the computers work on 0 and 1. Signal is there, it is 1. There is no current, no electrical signal, it is 0. Similarly for optical computers, it would be with respect to light, 0 and 1. For crystal growth also, because light is life, that everybody knows. If there is no sun, there would be no life. So all the life is due to light. Life means everything is growing also due to light. Now using this simple thing, if we use laser in doing many other things, we can see some results. So in live things, even neuron means the cells of your mind, brain, not mind, brain. The cells of brain can be grown, they can be studied using lasers. They can follow laser light. If a laser light is shown on them, then the neuron can grow in that direction. Similarly, lasers can be used in crystal growth also. Now a little different thing. Now you have lasers. You may have 2 milliwatt laser, you may have 10, you may have 25 or even more. And with free electron lasers, you can have very high intensity lasers. Now when this high intensity is shown on some crystal, some material, what will happen? What do we expect? So somebody is asking, optical properties of a medium depend upon intensity of radiation. Somebody is asking, can this happen? So this will appear a weird question, that how the optical properties can change due to intensity of radiation. Everybody will say no. The medium is medium. Its property will not change. But this answer was true before the laser era. It was true in the pre-laser era, not in the post-laser era. You can see here one of the interesting example. This laser is coming of frequency omega. Okay, what is this? This is dipole. These are dipoles. So this omega is coming, falling on these, and what is coming out? It is coming out 2 omega. Frequency is doubled. The color has changed. How the color has changed? There is nothing, no other optical components present here. Only a material and a laser. Laser is shining upon the material. Coming out, frequency has doubled. Color of the light has changed. This we never knew earlier. Initially, we have been asked by our teachers, and we keep asking to our students that suppose a red color light is coming inside a prism and it is leaving, will the color of the light change? This is a common question in bio. So students has to tell that no, the color will not change, because the frequency will not change. It is the fundamental characteristic of the radiation. It will not change. The refractive index may change. The wavelength may change. Therefore, the velocity may change. But the frequency will not change. Whereas in case of high intensity laser, we see that the frequency has also changed. And this is termed as frequency doubling. Second harmonic generation. There can be 3 omega also, then we will call it third harmonic generation. It is, if it is doubled, we call it. So for knowing the concept, either you say second harmonic or third harmonic or nth harmonic, but you should know that a particular intensity can create something in the material which will change the color of the radiation. IR is converted to visible. You can see that. If this is IR radiation, frequency has been doubled and it has been converted into visible. So 1064 nanometer output from ND arc laser, the IR can turn to green 530 nano. इसको डबल करिए 1064 को, फ्रीक्वेंसी को डबल करने का मतलब इसका लेंथ वेवलेंथ क्या हो गया 532 आधा इसका 532 and this is green. And if you start from 800 nanometer output from a titanium sapphire laser, which is very near to red, it will turn to 400 nanometer, that is the violet. It will become violet. So this you should always remember when two things of similar dimension, similar parameter, not the dimension in terms of x, y, z, similar magnitude I should say. If any parameter of two things is of similar magnitude, changes will happen. If they are very far from each other, that means one is very small, other one is very big, one is like ant, other is like elephant, nothing will happen. Elephant will never see ant, but elephant will always see an elephant because the magnitude is similar. So when the intensity of this radiation is so high that it could interact with the interatomic forces of the material, if it is disturbing the interatomic forces and the interatomic fields between these atoms, when the fields will get disturbed, something new will happen. And these dipole will start oscillating at very high frequency, maybe double of this frequency, maybe triple of this frequency, and you will get a radiation of another frequency, double or triple. This can also happen that you send two radiation on this side, one omega 1, another is the omega 2, both are of very high frequency. They will interact with the interatomic fields of this material and the dipole will start oscillating at omega 1 plus omega 2. And then you will not get a clear-cut harmonic, but you will get a higher frequency, which is omega 1 plus omega 2. And therefore, this is called mixing of frequency. Whereas earlier we never heard, without this laser and without this nonlinear optics, we never heard of mixing of frequencies. So doubling of frequencies, mixing of frequencies, and whatever you have not heard of till now, that is possible in nonlinear optics. This is called nonlinear optics. Nonlinear because linear means a straight line. You know that. If you see the output of a diode, it is nonlinear. So when you get that curve, when in the expression, in the equation, when A is directly proportional to B, you get a line, a straight line. Y is directly proportional to X. Yeah, Y is equal to MX. You get a line. But if Y is directly proportional to X square, then what happens? You don't get a line. You get a parabola. That means you get a curve. If it is proportional to X cube, you will get something other curve. If it is proportional to X square, A square plus BX cube, you will get some other curve. So when these polynomials come in, then there is not a straight line, there is some type of curve, and therefore we call it nonlinear optics. So what is the parameter which is going to do these things, square and cube, etc., and square of what? Which quantity? So square of electric field. The refractive index, earlier you knew that the refractive index is directly proportional to E. Or you have studied the equation P equal to chi E, where P is the polarization, chi is the polarizability, and capital E is the electric field. When you apply electric field on any material, that gets polarized. And it gets polarized according to its own property, the polarizability chi. But when you shine light of very high intensity from a laser, then this P is not chi E. Then this P will become P on the left side, left hand side. On the right hand side, it will be chi E plus chi of second order into E square plus chi of third order into E cubed, and so on. So this in the total theory, total calculation, you see that higher orders of electric field starts occurring, and that is the nonlinear effect. And due to this nonlinear effect, many new things are happening. One thing everybody should remember, that the non-linear optics, non-linear terms are not just an extension of linear thing, and so that you can neglect the square terms and compare to the single power terms. No, this is not the case. The single power terms are totally different and the high power terms are totally different. Those are very small, as if you consider the magnitude only, they are very small. But they should not be neglected because they both are not the same thing. Had they been same thing, then the smaller one could be neglected. But they are totally different. One is the linear and another is the non-linear. Non-linear is going to give you very new properties. So you will not neglect it. You have to study it as something very different. Another non-linear property we can see, just say you see this, which we were talking about in lunar ranging also, retroreflector. Ordinary reflection, the light is coming on this path, light is being reflected on this path. But in retroreflector, if the light is coming on this path, it will be reflected back on this path, on the same path. This is in retroreflector. In ordinary reflection, this happens, but for a particular case. What is that case? That is the case of normal incidence. If the light is incident normally on a surface, it will trace back its original path, but for normal incidence only. Whereas in this particular phenomena, which I am going to tell you, even at other angles, if the light is coming, it will trace back that path only. Here you can see it clearly. A regular mirror, light is coming normally, going back on it. Phase conjugate mirror, light is coming, going back on it, okay. But here you see, if it is in normal mirror, if it is coming at an angle, it is going away in that other angle. So you see it is a big difference in the path of these two, incident light and reflected light. But in the case of this mirror, where the non-linear thing is happening, the light is coming at an angle and going back on the same angle. Such mirrors are called phase conjugate mirrors. But these mirrors are not simply mirrors as if you are purchasing the normal mirror. These mirrors actually involve 3 laser light, 3 or 4 laser light, which are coming, they are changing the medium, something is happening inside the medium, and because of that happening, this laser light is being reflected on its original path. So that phenomena is called phase conjugation. And anything which is reflecting, since it is reflecting, we call it mirror, but it is not a mirror in the conventional sense. But since it is reflecting, we borrow the name mirror. So we call it phase conjugate mirror. And the phenomena is called phase conjugation, or more clearly, it is called optical phase conjugation. So it has tremendous uses and is quite difficult to achieve. One of the interesting use I can just correlating that before your science could get it, actually the theoreticians, the mathematicians, they are way ahead of physicists. They are at least 100, 200 years ahead of physicists, and they see the things much before. So this is an interesting example. Let us read it first. Looking into a conventional mirror, one would see one's own face. Whereas looking into a phase conjugate mirror, one would see only the pupil of the eye, because the light going to the mirror will come on its same path. So you can't see any other thing. Eye will see, but the light going from the leg is coming to the leg. So how will the leg see? Leg can't see. So you'll not be able to see the leg. Only eye can see, therefore you will see eye only. if the light is coming back from the phase conjugate mirror. This is an example, interesting example. Many of you have read this book, chapter Alice in Wonderland. So the person who wrote Alice in Wonderland, the Lewis Carroll, he was actually a mathematician, not only a fiction writer. So he gave all these diagrams. See, this cat is looking into the phase conjugate mirror and is able to see the eye only. Whereas this girl is looking into the phase conjugated mirror, or instead of her face, she is seeing the back of this. Whereas these are normal mirrors. So this is one interesting example so that you can always remember optical phase conjugation. Another thing in nonlinear optics is Soliton. Soliton communication is being operated in US for I think more than 10-20 years. It has already been operated. 10,000 kilometers of communication line has already been laid down way back. I think when the whole of the India will have fiber optic link, this Soliton will come to India, and again everything would be digging of roads will start again. So what is this? This is Soliton, again a combination of two words. Solid means solitary. Solitary, this is one single solitary wave. You can see this canal full of water. You can see the water is here, and here you see a hump. A single hump, just like a sinusoidal wave. You see the single humps of the sine wave, see the only one portion, not the other portion. So you see it is a single hump coming here and it is again going down. This single hump is so interesting and so strengthful, so strong that it keeps on moving throughout the canal and it is not destroyed. So once someone, John Scott Russell, saw this thing in the canal, and then he followed this particular thing throughout the canal on his horse. He kept on following, and then there was a change of path and he could not go beyond that. But through a long distance, he could see this Soliton going, but it was not getting destroyed. Now these days, again a canal was built and this Soliton was recreated. See, this is being recreated. People are seeing it. A Soliton has been recreated. It is like this. So it is not a sine wave. You know that because sine will go downwards also. It is a hyperbolic secant. It is hyperbolic secant, sec hyperbolic. Sec hyperbolic function है ये. इस Soliton जो है, it is very strong. It will not get destroyed. It will go on moving like this since it is a solitary wave. We are used to write like we write photon, plasmon, phonon. Similarly, we are writing it as Soliton. So it is solitary wave moving, and it takes the form only when there is a certain level of intensity. So with lasers, we can have Soliton if the laser is of very high intensity above the critical intensity of the Soliton. Critical intensity which is required to make a Soliton. So Soliton communication links are already established in US and may be established in the rest of the part of the world. Laser-induced background spectroscopy, that is another application of lasers. So lasers have already made space in every field. In the field of material science, they can be used as for breakdown spectroscopy, which is called LIBS, LIBS, laser-induced breakdown spectroscopy. The emission spectra of the plasma plume generated by a focused laser beam on a target have attained great prominence in recent years. I have told you that the laser beam is focused. It is highly directed. If you focus it on a material, if you want to focus it in 1 millimeter only, you can do that. You can, when you will focus, the focused portion will get heated and a plasma will be coming out from that heated portion, and we call it plasma plume. So that can be used in material science. Now this ablated material, ablated means heated. Material cools down after a few microseconds of the laser impact to give emission from atoms and ions that constitute the target. Now since if it is giving emission, that plasma was having atoms and ions, and the color is coming out, some emission is coming out. So if it is an alloy, suppose you have you got some material, you don't know it is a single metal or it is an alloy or what is mixed in it. So you will have to go for laser induced breakdown spectroscopy. Focus the laser beam, it will get melted. Atoms and ions will come out in the form of plasma. They will give emission. That emission will be recorded, and you can compare it with the characteristic emission of the atoms and ions. And you can know the composition of that particular sample. It can be used quantitative and qualitative for both type of analysis of any kind of material, whether solid, liquid or gas. It is a non-contact and remote method of detecting various kinds of trace materials. बहुत ही कम मात्रा में अगर हैं trace materials, so that also you can know, including the explosives also. It has been increasingly used after the advent of CCD detectors, which have much faster response than the photographic films. So you know very well photographic films are not being used now because of we have CCD detectors, charged coupled device detectors these days. So lives in water, finds direct in water means you are keeping the material in water and doing the lives experiment. Finds direct application in non-invasive intraocular surgery, laser-induced lithotripsy, and angioplasty. Another use, this is the pulsed laser deposition of thin films. Now you know everything, our integrated circuit, that everything is in the form of thin films of the material. Our mobile, calculator, computer, everything is having thin films. Those thin films can be made using pulsed laser deposition. Why pulsed? Because in pulse we can get high energy and we can adjust the duration of pulse also. Shape also can be adjusted, which will lead to different properties of the films. So when we focus, see here, the laser is coming from this path, it is being reflected by the mirror, it is going inside through a window inside the vacuum chamber. This is the vacuum chamber. A high vacuum has been created in this chamber and some material is kept over here. The material you want to make a film of. So the laser is coming, it is shining on this particular material in a very small area, say 1 millimeter or 2 millimeter. And the localized heating is happening here. And the material is ablated. That ablated material is a plasma, and that plasma plume, see this plume, starting from here and coming up till here. This may be 5 or 6 centimeter distance, not more than this. So it is coming here. Here you have put a glass or a quartz or a steel, whatever substrate you want, and this plume touches that, and whatever atoms or ion it is carrying, it gets stuck on this substrate. And after certain time, you will set a time, you will set a pulse rate, and you will get a film deposited on this substrate, and you can study it. However, this is a big arrangement. Here are several materials. You can move this carousel and you can shine the laser light on other material. So a layer of thin films can also be deposited. Everything is computer controlled. So this is pulse laser deposition, is a very sophisticated technique, and a krypton fluoride laser, the Alzheimer laser, pulse laser is being used here, which is having a wavelength of 248 nanometer. That means it is of very high energy, and a pulse width of this particular laser is having a 30 nanosecond, which can be changed also. And due to changing of this, the properties of the films would change. So laser can be used like this also. Pulse laser deposition of thin film. It is sophisticated, and a very important result of such type of deposition is that the stoichiometry of the material is maintained. Stoichiometry means the chemical formula or would be maintained, or suppose you have taken an alloy or you have taken a material which has something doped in it, then suppose you have doped 1% in it and 99% is the material and 1% is the dopant, and you have properly doped and prepared a pellet out of it, and you are doing this experiment, the film you are getting at last will also have that ratio, the 99% and 1%. That means the stoichiometry is maintained. This ratio is very difficult to maintain in other type of deposition of thin films, but here it is maintained. So pulse laser deposition has a nice property that it maintains stoichiometry in its films. Now, after telling so much advantages and uses of laser, we should not undermine this important thing, that the laser safety. Generally, Indians, they do not think, they are very excited and they never think of safety, and they just jump into doing experiments with lasers. But any lab which is having laser, any lab of yours which is having lasers, they should have laser safety material also. Like laser goggles are also there. Since the beam from a laser is focused by the lens of the eye to a very small spot on the retina, direct exposure of even low power laser, ये बहुत ध्यान देने की बात है, even 2 milliwatt, 1 milliwatt laser can damage the eye. With pulse laser, because pulse laser are of very high intensity, even stray reflections coming from anywhere else can be dangerous. So all these precautions should be taken. All these things should be kept on. You can put it on your doors or laboratory door, etc., so that anybody may not get this damaging radiation by accident. Next we come to holography. Holo means complete, graphy means writing. Complete writing means all the dimensions are being shown in that picture, 3D picture, and this is possible due to laser. The holography itself, the concept, was actually discovered earlier, but it could be realized only after the advent of laser. It is a two-step process. One is recording, other is reconstruction. In one step, you will not be able to see anything. When you will record, you will see only fringes there on the film, because the interference is taking place, and interference fringes will be seen and nothing else. Suppose you are recording your face, you will see the interference fringes, not your face. But when you will do the next step, that is the reconstruction, where diffraction phenomena is taking place, then you will be able to see your face. And some type of white light hologram you have already seen on many commercial products which is used for authentication. Many universities are putting hologram on their mark sheets for the authenticity. So that is the white light hologram. But in a general, white light, it can be seen in the sunlight. But actual holograms, they cannot be seen in the white light. You require to know the wavelength by which it has been made. Only then you can reconstruct it. Excuse me, please वो बंद कर दीजिए. The source, in this source there is an object wave, which is called the signal wave coming from the object, and other is the reference wave. Reference wave is not disturbed. Object wave gets disturbed due to object coming from the object, and both these two waves, they interfere at the recording medium and they give interference fringes. Now complete information is recorded as interference fringes. The spacing between them, it is just an example that can be 10 to the power minus 3 millimeter. The spatial resolution of the recording material may be 1000 lines per millimeter. It is just an example. Now you can see these two photographs. These are holograms. It appears that you are seeing a real thing, not the picture, because this is a hologram. Now you see here, this is a hologram of Professor Gabor. Professor Gabor was a Nobel laureate who has been awarded the Nobel Prize for discovering this holography. So it is his portrait, holographic portrait. And this was produced by some other scientists, Lenhart and McDonald, in 1971 using a pulsed ruby laser. And I am lucky enough to have worked under the supervision of Professor T.P. Pandya, whose photograph is this. And he was a student of this Nobel laureate, Professor Gabor. And this is the holographic portrait of him. In photograph, you have 2D recording of a 3D scene. Only intensity distribution is recorded. In a developed negative, the optical density of each point is a function of optical energy received there. Means whatever optical density, optical energy is received, that is recorded on the photograph. And you get a two-dimensional photograph only, whereas the scene was three-dimensional. You don't have any idea of the depth of the things, of the width of the things, you don't have any idea. The photosensitive medium is sensitive only to the intensity. Please note this. Photosensitive medium is sensitive only to the intensity. And hence, while recording a photograph, the phase is lost. You know that there are some important parameters of light. One is intensity, other is phase, other is frequency, other is polarization, and so on. At least 5 parameters. So if you lose the information of phase, you will lose the information of the third dimension. You will know about X and Y, you will not know about Z if you lose the phase. So in photosensitive medium, only intensity is important, phase has no meaning, and we lose the information of phase, and therefore we could not know the depth of the scene. To record the third dimension, one needs to record depth. Depth record karna means it implies recording of phase, because phase is related with the path difference. And path difference occurs due to depth. One light is coming from the front row and the other is coming from the last row. So there is, if in a class you are making a hologram of a class and there are 10 rows. So students are sitting on all the rows. So from the first row the light is coming. From the 10th row also the light is coming. From the 9th row also the light is coming. So all these light rays are traveling different paths, and that gives rise to different phase. And if this phase is not recorded, the depth of the class cannot be recorded. To record the phase, we have only one optical phenomena, and that is interference. So we record, we have two, I'll show you the, perhaps I have a photograph. Yeah. Yes, you see this? Here there is a source. It is a laser source. We have expanded the beam using some microscope objective. We have expanded the beam. This expanded beam is coming on this side. Here in between there is a mirror. Part of the beam is incident of the mirror being reflected, and part of the beam is going to the object. And from that object, since the object is not a regular thing, it may be having hills and valleys. So the light is being scattered all over. And the reference wave is also coming, object wave is also coming, and these two will interfere, and the interference pattern will be recorded on this plate, because this plate is having a photosensitive medium over it. When the interference pattern means changing intensity, and that changing intensity will be recorded over this. Nowadays we are having digital holography, so we are not using photographic plates. Instead we are using CCD. Okay. Now on this photographic plate the hologram has been recorded. First step, it is interference fringes. In the next step, reconstruction will be done. For reconstruction, you will keep the hologram like this and you will shine a light. What properties of light are important? This light should be same as that of your reference wave. This reference wave, see this reference wave, this reconstruction wave, they are parallel, you are seeing. Parallel means they are falling on the same angle. The first thing is they should fall on the same angle, they should have the same frequency, same polarization, everything should be same. Only then you will be able to reconstruct. That is the plus point of hologram. And that's why it is used in security purposes. It is used in defense also. It is used for coded things also. Because nobody could, you can have the hologram, you can steal the hologram, some confidential hologram, but you will never be able to reconstruct it. You will never be able to see what is inside it, what is recorded on it, unless and until you know all the parameters of the reference wave, like frequency, polarization, angle, etc. Now if you know it, you shine it, and you will see that a real image of the object is reconstructed here, and a virtual image is reconstructed at the same place where the object is kept. It is kept on the axis. You see that the virtual image is kept. Virtual is reconstructed at the same place, and the real is reconstructed at 90 degrees of that. In another reconstruction, you take conjugate wave of the reconstruction wave. It was falling from this side. Now you are falling it from this side. So what is happening? The position has been changed. The real, everything has moved by 90 degrees. The virtual image was here. Now it has moved by 90 degrees and come to this place. And the real image was here. It has moved by 90 degrees and come to this place. So there are two methods of reconstruction, one with the original wave and other with the conjugate of the original wave. So this two-step process, either you take this or this, first, second step, or first and second. So this two-step process is called holography. And now interference fringes are a photoplate wala, I am not telling you because nowadays it is not being used. You can use holography to make optical elements, like if you want to make a zone plate. If you want to make a zone plate, then you can make a hologram of a point source. If you make a hologram of a point source, the hologram will appear as like this, like a zone plate. It will have rings, concentric rings, and it will behave as a, when you will reconstruct it, it will behave as zone plate. So very good use of holography is in holographic optical elements, which is called HOE, because instead of real optical elements, like lens or a real optical setup, you can have a hologram of the whole setup, which would be very easy to carry from one place to another, very light, very easy, no glassware in it. So holographic optical elements are also in use very much for complicated optical setups. They have high information capacity because you can record several holograms on the same photoplate, by using different angles of reference wave, different wavefront shapes. So if you change the property of the reference, one of the property of the reference wave, entirely new hologram will be recorded on the same photographic plate, and it will not disturb the reconstruction. You can have hundreds of holograms, one over the other, on the same photoplate, and when you will reconstruct, they all will appear separate. There will be no mixing. And for example, you can see 100 centimeter square, yani 1 meter square may contain Encyclopedia Britannica, the whole book, over this much area. The next thing, even a broken piece gives complete information, because you know that if the lens is broken, only the intensity of the image will go down and the information will not be lost. So the time is to finish, so I should run on to LIGO. This is the hologram.
Yes, ma'am. Yes, ma'am. Yes, please.
Okay, this is the hologram of a bullet in flight. Computer generated holograms, diffraction gratings, HOE, I already told you. Neural networks. Holographic neural networks are attractive because they offer large storage capacity as well as parallel access and processing capabilities. तो इसको सब छोड़ के LIGO पे आ गया. LIGO, इसमें the diagrams are via courtesy internet. Diagrams have been taken from the internet. The LIGO का full form है the Laser Interferometer Gravitational Wave Observatory. LIGO has 3 gravitational wave detectors. 2 are in northwestern USA and 1 is in southeastern USA. Proposed LIGO India. LIGO India project aims to move one advanced LIGO detector from USA to Bharatvarsh. LIGO India project is envisaged as an international collaboration between the LIGO laboratory and 3 lead institutions in the Indigo consortium. Indigo जो है वो India LIGO है. कौन से 3 है? इंस्टीट्यूट ऑफ प्लाज्मा रिसर्च गांधीनगर, आयुका पुणे, RR-CAT इंदौर. LIGO detectors in USA and Virgo in Italy would form a single network and would be operated jointly by Indigo and the LIGO lab. LIGO lab would provide the complete design and all the key detector components. Indian scientists would provide the infrastructure to install the detector at a suitable site in India. ये देखिए, ये वहाँ का है, यूएस का है. मोदी जी और वहाँ के ओबामा जी बात कर रहे हैं इस LIGO पे, और तब से ये LIGO आया. LIGO क्या है? ये एक इट इज सिंपल माइकलसन इंटरफेरोमीटर, जो हम सब पढ़ चुके हैं. You can see there are 2 arms. This is one arm. Here is the mirror. This is the other arm. At this end there is a mirror. Here also you can see one arm of several kilometers, say 4 kilometers. One arm. This is also 4 kilometers. And a mirror is at the end. And the mirrors reflect the light. They come here and they interfere here, like in Michelson interferometer. And if any gravitational wave is coming from space, it is coming, the wave is coming, and it is disturbing the mirror. So a little displacement will happen and that displacement will show a phase shift in the interference fringes which is obtained here. And that phase shift is so small, it is 10 to the power minus 24 type. 10 to the power minus 24. So that small phase shift can also be recorded just because of having a big arm, long arm. So that can be done. The experiment proposed in India is having a 4 kilometer length, and it can detect small changes 10 to the power minus 23 के order का. LIGO India would enable to localize gravitational wave sources in the sky. Source कहाँ से आ रहा है? Suppose it is coming from a distant galaxy, a distant star. So you will be able to locate. LIGO India will be able to look. Because how it will be able to locate? Why India has to be involved? Because you need different locations, and the light reflected from different locations, if you combine, then you pinpoint at the location. You can pinpoint on the star. So earlier it was in USA only, but they need to observe from some distant place also. So perforce they have to involve some other nations also, and India is one of them which has been chosen. You can see this, just like sound waves are traveling. Similarly, gravitational waves are also traveling. You can see EM energy travels like this, everybody knows. And the gravitational waves can be seen like this. Suppose these are two binary stars. They are revolving about each other. Rapid movement of massive objects creates ripples in space-time. इसलिए because we know space-time is x, y, z, t. And this is the fabric of cosmos. इसे हम हिंदी में बोल के बताना चाहेंगे. ये खाली ये अंग्रेजी से नहीं आया है. हिंदी में हम कहते हैं देश का मतलब x, y, z. काल का मतलब t. परिस्थिति का मतलब कंडीशन. सो देश काल परिस्थिति इज वेरी इंपॉर्टेंट. वही चीज यहाँ कही गई है कि x, y, z, t is the fabric of cosmos. It was predicted in general theory of relativity. Gravitational waves do not travel through space-time as such. Wave खुद नहीं आती है. The fabric of space-time itself is oscillating. Just like if you see a badminton thing, the net of the badminton. If you just throw your what you call, I don't remember the name, shuttlecock. If you throw the shuttlecock on the net will vibrate. Similarly, when two massive objects are moving, this net fabric XYZT, which you are not able to see, but it is there, it starts oscillating, and that oscillation comes to us, even on the earth. You can see if some massive object, suppose our earth, it is actually there, XYZT. This net is XYZT, and the earth is put in that net. So this type of dip would be created, and this dip would oscillate and go somewhere very far, because it is you know the wavelengths which are very long, they can travel very far. The example is radio communication. Radio waves have very large wavelengths of meters in magnitude, so they can travel very far up to what you call means several layers of atmosphere. They can go very up, and then they will be reflected, and your communication will be taking place. So gravitational waves are also of very large wavelength, and therefore they travel from one place of the universe to other place of the universe. So there are many sources like in spiral gravitational waves. Continuous gravitational waves are produced by massive astrophysical systems that have a fairly constant and well-defined frequency. Examples are binary star, black holes. In सबसे आती हैं. There can be burst, like a supernova burst, like a gamma ray burst. Then again the gravitational wave will come. The GW spectrum, gravitational wave spectrum. Astrophysical electromagnetic waves are incoherent and have wavelengths typically much smaller than their sources. Means sources are very big, ranging from a few kilometers down to subnuclear wavelengths. Gravitational waves are coherent. Coherent होना बहुत important है, and have wavelengths larger than their sources, with wavelengths starting at a few kilometers and ranging up to the size of the universe. Wavelength देखिए कितनी large है. The wavelength is so large that is comparable to the size of the universe also, and therefore it travels. So for persons who are interested in LIGO or who want to tell to their students about LIGO, I think this lecture was being recorded. It would have been recorded, so you can have that recording. You can have a print. You can just have a screenshot also immediately. You see that first joint detection of LIGO and Virgo. Virgo is in Italy. The 3-detector network delivered a significantly better source localization and access to polarization information. वो 3 जगह होने से ही अच्छा हो पाया. If we have more places, तो we will be able to detect local. We would be able to know the location of the source, the celestial source in the space even more precisely. You can see on August 14, 2017, only 4 years back, the LIGO detectors in Hanford, Washington and Livingstone, along with Virgo in Italy, detected a signal from coalescence of 2 black holes with masses 31 times and 25 times of the mass of the Sun, our Sun, merging into a more massive black hole that is 54 times the mass of the Sun. इसको जोड़ दें अगर हम 30, 20, 50, 56 हो गया, but some mass is always lost when a binding is occurred. So 54 times the mass of the Sun. This is the first detection by the joint LIGO-Virgo 3-detector network. A network of detector enabled localization of the source through triangulation. Triangulation means at 3 places because three detectors were there. So you were able to locate it correctly and gave access to the polarization of the waves. The planned LIGO India detector promises many-fold improvement in source localization accuracy as compared to the LIGO-Virgo network. Means India के आ जाने से it will be even better located. So students should come into this field. Parameters of the detected signal, masses of the hole, distance of the event, you can see 1.8 billion light years away. Date of arrival 14 August 2017. Time of arrival 4 p.m. It was detected. Energy released in the form of gravitational wave was equivalent to 2 solar masses. 2 solar masses. इसको convert करिए by E equal to mc square and you'll see how much the energy was released. Source localization accuracy 60 square degree compared to 1160 square degree with 2 detectors. With 2 detectors there was a accuracy of means this much, and it is now pinpointed. 60 square degree is very small, and when the India will also come in, it will start commissioning it. It will commission its detector. Then even smaller you will be able to localize, even less than 60, maybe 30, 20 or whatever. So Nobel Prize winners in physics announced in Stockholm. Yeah, you can see the picture nicely here. This is only a Michelson interferometer, light coming from this side, light coming from this side, which was being splitted. This was the source. This is beam splitter. Light is going to both the mirrors, coming back and giving you the interference fringes. Impact on science would be great. In optics, lasers, gravitational physics, astronomy, cosmology, computational mathematics, every field would bloom. Every field would bloom due to this. It is coming in India. That is a great boon for us. Industry will also get impacted very nicely because they have to make high-end engineering requirements will be there. They have to make it, they have to machine it, and optomechanical things will get a very big boom. Education also, since cutting-edge project in our country will provide opportunity to researchers, to inspire students, young scientists for choosing experimental physics and engineering physics as well. This is very important. People are not taking engineering physics. Either they take engineering or they take physics. But engineering physics as a whole, as a combined, would be very useful. The LIGO India project involves high technology instrumentation which will escalate technological developments in our country. यहाँ पे अपने कंट्री का पुराना याद दिलाना चाहते हैं. Astronomy is one of the oldest sciences as mathematics, and you should listen to the lecture Aryabhat Astronomy, the lecture by Professor R. Subramanian. He is in IIT Bombay and he is working on it. So you just go on the YouTube, you type IIT Bombay R. Subramanian, and you will see several lectures of him telling about how accurate our astronomy was. And perhaps you have gone there, and if you have not, please do visit this Jaipur Observatory, which stands intact more than 1500 years. After 1500 years, guiding us about the celestial bodies and their movements. I would like to tell you that on these walls, like this, on these walls, you can see the graduation marks, whatever you see on a scale. All these graduation marks have been taken from these places. They have not come from the West. I would like to emphasize, please go there and see. I have photographs and last photographs. All those marks are like centimeter, inch or anything. All those are marked over here. In cement, in concrete. In the past 400 years, we have studied almost every available window of the electromagnetic spectrum, resulting in an ocean of knowledge about the universe. Today, we are on the edge of a new frontier in astronomy, that is the gravitational wave astronomy. Since the universe, अभी तो हम एक्सरे से ही पढ़ते रहते थे, एस्ट्रोनॉमी एक्सरे भी देखते थे और रेडियो वेव्स और ये सब देखते थे, but now we are on the new frontier, that is the gravitational wave astronomy. Since the universe is more transparent to gravity, this study will explore. More transparent to gravity means gravity related things can travel in the universe from this place to that place more easily. Therefore, this study will explore an unknown aspect of the universe and can be named our attempt to build the first gravitational wave telescope. We can do this because India is already being included. Now, research opportunities for students, you can take a screenshot also for this research opportunities for students. These opportunities are available for undergraduate and master students with LIGO India at IUCA Pune, RRCAT Indore, IPR Ahmedabad, as well as with the LITRD laboratories at various institutes, and this is the link for taking it, showing it. LIGO India is a multi-institutional mega science project which will be part of the international network. Everything has been approved. I think all technical, all administrative things have been done. Now the technical things have to be started. And with this, I would like to, as I have gone past 10 to 12 minutes beyond my time, I would like to stop here. And thank you again to the organizers.
Thank you, madam. Thank you for such a wonderful lecture. We learned a lot of things, starting from 3-level, 4-level laser system to holography, and then laser interferometer based gravitational observatory. Thank you, madam. I would like to ask participants if there are any questions, 1 or 2 questions we will take. They can unmute themselves and ask the question. Mr. Mayur, one small question.
Yes, sir. Ma'am.
Are you able to see the slides?
Yeah.
Yes,
yeah.
ma'am.
Now
Acha.
your desktop is seen, ma'am.
Why they have maintained the arm length 4 kilometer?
Now slides are visible.
They have maintained long lengths because only then you will be able to detect small distances, because their requirement is to detect a change of the order of 10 to the power minus 23. So if you take a small Michelson interferometer, then how will you be able to detect that? If there is a greater path length, then even small changes could be detected.
Okay.
It may be greater than 4 kilometers.
Okay, thank you, madam. Now I request one of our participants to propose vote of thanks. Dr. Anil Nikam, I request him to propose vote of thanks. Nikam, sir, please. Propose vote of thanks. Nikam, sir, am I audible?
You are audible.
Yes, sir. He is having some connectivity problem. Now I think we are connected with him. Nikam, sir, you are not audible. I think we have some technical problem.
Sir, I will take.
Go ahead, Dr. Ajay.
Okay,
Yes.
okay, thank you.
राज सर एक मिनिट त्यांनी जॉईन झाले. राज सर.
Okay.
Sir, please. Nikam, sir, please start.
Yes, sir. Good evening, all. As an outskirt, I, Mr. Anil Nikam, on the behalf of organizing committee of this FDP, would like to sincerely thanks or express my sincere gratitude to Dr. Anchal Srivastava ma'am for delivering a session on lasers, including the types as well as applications, holography and LIGO. Thank you, madam. Also, I would like to thank Dr. Abhijit and all the organizing team for arranging such a wonderful FDP on the photonics. Thank you all.
Thank you, madam. Thank you, Nikam, sir.
Thank you. My video